Your body is running on the wrong fuel right now. Not because you made a bad choice this morning, because for 50 years, the wrong thing was blamed. In 1980, the United States government told over 200 million people to cut fat out of their diet. Dietary guidelines, food pyramids, low-fat everything. The food industry listened. They pulled the fat out of thousands of products. And then they had a problem. Because fat carries flavor. Remove it, and the food tastes like nothing. So they replaced it with sugar. Over the next 4 decades, obesity rates in the United States nearly tripled. Type 2 diabetes rates quadrupled. Non-alcoholic fatty liver disease went from a rare condition to affecting roughly 1 in 4 adults worldwide. Something didn't add up. So which one is actually worse for your body? Which one does your liver turn directly into fat? And which one physically changes how your brain responds to food? By the end of this video, you're going to understand exactly what happens inside your body when you eat sugar, and exactly what happens when you eat fat. Not the headlines, the actual mechanisms. You'll know which one drives insulin resistance, which one your liver processes differently than every other cell, and why the answer to this question changed the health of an entire generation. It's going to be a metabolic one, so let's jump into this anatomical and physiological awesomeness. First, we need to understand how we got here. In the 1950s, an American physiologist named Ancel Keys proposed what became known as the diet-heart hypothesis. The idea was straightforward. Dietary saturated fat raises blood cholesterol. High blood cholesterol causes heart disease. Therefore, eating fat causes heart attacks. Keys ran the 7 countries study, one of the most influential nutrition studies ever conducted, and his conclusions shaped public health policy for the next half-century. But there was a competing hypothesis at the time. A British physiologist named John Yudkin argued that the real driver of heart disease and metabolic dysfunction was not fat, it was sugar. He published a book about it in 1972, and his work was largely dismissed. Here's what we learned much later. In 2016, researchers at the University of California, San Francisco published an analysis in JAMA Internal Medicine of internal documents from the Sugar Research Foundation. Those documents showed that in 1967, the sugar industry paid 3 Harvard scientists the equivalent of about $50,000 in today's money to publish a review in the New England Journal of Medicine. That review downplayed the link between sugar and heart disease, and it emphasized fat instead. The funding was not disclosed. That review helped shape decades of dietary advice. Now, this doesn't mean fat is harmless. It doesn't mean Keys was entirely wrong. Science is more complicated than a single villain. But it does mean the question was never settled the way the public was told it was. So let's look at what these two things actually do inside your body. Start with fat. Dietary fat is made of molecules called triglycerides. A triglyceride is 3 fatty acid chains attached to a glycerol backbone. When you eat fat, enzymes in your small intestine break those triglycerides down. The components get absorbed through the intestinal wall, reassembled, and packaged into transport particles that enter your lymphatic system before reaching your bloodstream. Fat is not just fuel, it's structural. Every single cell membrane in your body is built primarily from lipids. Your brain is roughly 60% fat by dry weight. Your body requires fat to absorb vitamins A, D, E, and K. It requires fat to produce steroid hormones, including testosterone, estrogen, and cortisol. Essential fatty acids like omega-3 and omega-6 cannot be synthesized by your body at all. You have to eat them. Fat is also the most energy-dense macronutrient, 9 calories per gram, compared to 4 for carbohydrates and protein. And critically, fat does something sugar doesn't do well. It makes you full. When fat reaches your small intestine, it triggers the release of a hormone called cholecystokinin. Cholecystokinin slows gastric emptying and signals satiety to your brain. Fat also stimulates the release of peptide YY and GLP-1, two more satiety hormones. This is why a meal with adequate fat keeps you full for hours, and why a low-fat meal often leaves you hungry again quickly. Now let's look at sugar. And this is where it gets interesting, because not all sugar is processed the same way. Table sugar, or sucrose, is a disaccharide. It's made of two molecules bound together, one glucose, one fructose. High fructose corn syrup is similar, just with a slightly different ratio and the molecules not bound together. Glucose and fructose are both sugars, but your body treats them completely differently.
Glucose can be metabolized by virtually every cell in your body. When glucose enters your bloodstream, your pancreas releases insulin. Insulin allows cells throughout your body to take glucose in and use it for energy. Muscle cells use it, brain cells use it, fat cells use it. The demand is distributed across your entire body. Fructose is different. Fructose is metabolized almost exclusively by your liver, not your muscles, not your brain, not distributed across trillions of cells, concentrated in one organ. And this single anatomical fact explains most of what follows. When you consume a large amount of fructose, your liver has to process all of it. And once your liver's immediate energy needs are met and its glycogen stores are full, it converts the excess fructose into fat through a process called de novo lipogenesis. That phrase literally means new fat creation. Your liver builds fat molecules out of sugar. Some of that fat gets exported into your bloodstream as triglycerides. Some of it stays in the liver. And when fat accumulates inside liver cells over time, you get a condition called non-alcoholic fatty liver disease. Here's the part most people find surprising. Non-alcoholic fatty liver disease is now estimated to affect around 30% of adults globally. It's called non-alcoholic because it looks nearly identical to the liver damage caused by chronic alcohol consumption. But it occurs in people who drink little or no alcohol. The mechanism is remarkably similar. And that's not a coincidence, because ethanol, the alcohol in drinks, is also metabolized primarily in the liver, and it also drives de novo lipogenesis. In terms of how your liver handles them, fructose and alcohol have more in common than most people realize. Now, an important clarification. This does not mean fruit is dangerous. Whole fruit contains fructose, yes, but it also contains fiber, water, and a relatively modest total sugar load. The fiber slows absorption dramatically. Eating an apple delivers fructose to your liver gradually over an extended period. Drinking a large glass of apple juice delivers a concentrated dose in minutes, without the fiber. The dose and the delivery speed matter enormously. A single 12-ounce can of regular soda contains around 39 grams of sugar. The American Heart Association recommends a daily limit of 25 grams of added sugar for women and 36 grams for men. One can exceeds both. And the average American consumes approximately 17 teaspoons of added sugar per day. That's around 71 grams, roughly double the recommended limit. But the liver is only the first problem. Now we need to talk about insulin. Every time you consume glucose, your pancreas releases insulin to move that glucose into your cells. This is a normal, healthy process. It's supposed to happen. The problem is frequency and magnitude. When blood glucose spikes repeatedly, day after day, year after year, your cells are exposed to high insulin levels almost constantly. And over time, those cells begin to respond less effectively to insulin's signal. This is insulin resistance. Your pancreas compensates by producing more insulin. Blood glucose stays normal for a while.
This phase can last years without symptoms and without showing up on a standard glucose test. Eventually, the pancreatic beta cells that produce insulin begin to fail under the sustained demand. Blood glucose rises, and that's when type 2 diabetes is diagnosed. By the time most people receive that diagnosis, the underlying process has typically been developing for a decade or more. There's also a direct link back to the liver here. Fat accumulation inside liver cells impairs the liver's ability to respond to insulin. So the fatty liver caused by excess fructose actively worsens the insulin resistance driven by excess glucose. The two mechanisms feed each other. Now let's look at your brain. When you eat sugar, particularly in concentrated forms, it activates reward pathways in your brain involving the neurotransmitter dopamine. Specifically, it increases dopamine release in a region called the nucleus accumbens, which is central to motivation and reward learning. This is not unique to sugar. Food in general activates these pathways. That's evolutionarily appropriate. Your brain is designed to reward you for finding calories. But the intensity matters. Highly processed foods engineered to combine sugar, fat, and salt in specific ratios produce a reward response that natural foods rarely match. And with repeated exposure, the response can change. Some studies show reduced dopamine receptor availability in individuals with obesity, a pattern that has parallels with other reward-driven behaviors. Now, I want to be careful here. You'll see claims online that sugar is more addictive than cocaine. That claim comes primarily from rodent studies, and applying it directly to human physiology overstates what the evidence supports. Sugar is not pharmacologically equivalent to a drug of abuse, but there is something real happening. Sugar in liquid form is particularly problematic because it bypasses your satiety mechanisms almost entirely. Liquid calories do not trigger the same fullness response as solid food. You can consume 500 calories of soda and feel no fuller than before you started. Your brain simply does not register it the way it registers a meal. That's not addiction, but it is a genuine failure of a regulatory system that evolved in an environment where liquid sugar didn't exist. Now here's the part that changes the whole picture. Because if we stop here, the conclusion seems obvious. Sugar is the problem. Fat is fine. Eat more fat. That's too simple. And it's wrong in an important way. Because not all fat is the same. And one type of fat is genuinely worse than sugar by almost any measure. Trans fats. Artificial trans fats are created through a process called partial hydrogenation, where hydrogen is added to liquid vegetable oils to make them solid at room temperature. This gave food manufacturers cheap, shelf-stable fat with a long lifespan. The metabolic effects were severe. Trans fats raise LDL cholesterol. They simultaneously lower HDL cholesterol. They increase systemic inflammation. They impair the function of the endothelium, which is the inner lining of your blood vessels. And unlike almost any other dietary component, there is no established safe level of intake. The evidence became overwhelming enough that in 2015, the United States Food and Drug Administration determined that partially hydrogenated oils were no longer generally recognized as safe. They were effectively removed from the American food supply by 2020. The World Health Organization has called for their global elimination. So the answer to which is worse depends on which fat you're talking about. Saturated fat is genuinely contested territory. Several large meta-analyses published over the past 15 years have found weaker associations between saturated fat intake and cardiovascular mortality than the original hypothesis predicted. The 2017 PURE study, which followed more than 135,000 people across 18 countries, found that higher fat intake was associated with lower mortality, while higher carbohydrate intake was associated with higher mortality. That study was controversial. It has legitimate methodological criticisms. but it's part of a body of evidence that made the original consensus considerably less certain than it once appeared. Monounsaturated and polyunsaturated fats, the kind found in olive oil, avocados, nuts, and fatty fish, have consistently favorable evidence across essentially every major study design. So here's the honest verdict. Between added sugar and dietary fat as broad categories, the current weight of evidence suggests that added sugar, particularly fructose in liquid form and in large quantities, does more measurable metabolic damage to the average person. It drives fat accumulation in the liver. It contributes directly to insulin resistance. It bypasses satiety regulation. And unlike fat, it provides no essential nutrients whatsoever. There is no biological requirement for added sugar. Zero. But artificial trans fats were worse than both. They were simply removed from the food supply, which is why they no longer appear in this comparison for most people. And that reveals the pattern underneath all of this. The question was never really sugar versus fat. The question was whole foods versus industrially processed ones. Nearly every food that delivers a large dose of added sugar is processed. Nearly every food that delivered dangerous trans fats was processed. The fats with the strongest evidence for harm were manufactured. The fats with the strongest evidence for benefit come from foods that existed before food science did. For 50 years, we argued about which macronutrient to blame. And while we argued, the actual variable that changed most dramatically in the human diet was how far the food traveled from its original form before reaching the plate. Your liver doesn't read headlines. It responds to what arrives, in what quantity, at what speed. And now you actually understand what it's doing with both. Thanks for watching, everyone, and we'll see you in the next video.